Beautiful talk by Moritz. There actually is something else to say about this problem, and Kunal will say something more about it.
This is joint work with Cynthia, Abradeep, and Lee, and the affiliations, as you might have noticed, are color-coded. So the main goal of the talk is to give a very simple algorithm and analysis for a differentially private PCA, and let me start out by defining what I mean by that. So this is the problem I want to look at. I have a matrix A. This is a m by n matrix, so think of it as m vectors in n dimensions. So each vector comes from an individual. So the first row could be Adam's Netflix movie ratings. The second row could be Moritz, and so on. And since we believe that people's preferences lie in some low dimensions, I want to find a low-dimensional subspace that contains all of these vectors. Well, I'll have some noise, so I won't get all of these vectors. I want to capture a lot of the variance of these vectors. So I want to find a subspace such that all of these vectors are close to this subspace. And I guess, as we know, this is done by the PCA. Now, one kind of nice thing about the PCA is that it gives me optimality for all possible, pretty much any measure you can think of. You can think of the Frobenius norm or the 2 norm and so on. So that makes it difficult to evaluate your approximate mechanisms because you have to pick a measure. In this talk, we'll be picking the measure which I find the most natural, which is the total amount of variance that you will capture. So I have these vectors. Essentially, there's the projection of this vector x1 onto the subspace. That's how much I'm getting out of x1. I'll take the squared projection, and I'll add that up over all the vectors in all the rows of my matrix. So I want to find a projection so that this quantity is as large as possible. Just the sum of the projections of the rows of the matrix, length squared. And actually, if you stare at it, it basically has this nice matrix form. But that's not really. Okay, so I'll also be assuming, and can think of this as just a normalization, that all my vectors are length 1, or at most 1. Good. So that's the problem. I have these vectors of length at most 1. I want to find a subspace in which all of them lie, or which contains as much of the variance of these vectors as possible. So as we know, this quantity is maximized by the subspace spanned by the top k right singular vectors of A, which are also the top k eigenvectors of A transpose A. So this pi k is what we'll be trying to approximate in this talk, while guaranteeing differential privacy. So obviously I won't define differential privacy, except to say that since the model we are looking at is where each person contributes a row, two matrices are neighboring if they differ in one row. Good. So why do we want to do this? I guess this is a useful subroutine in many algorithms. If we think of our xi's as kind of data which lies in a low-dimensional subspace plus noise, you want to eliminate noise to end up with a low-dimensional problem. This could help you both from a computational viewpoint, from a generalization error viewpoint, also from the privacy viewpoint, and so on and so forth. And in fact, this was a subroutine that was used by McSherry and Mironov in their implementation of a differentially private PCA, a differentially private recommendation system for the Netflix challenge. So, yeah. Okay. So this is the problem we'll try to solve. In this model of privacy, there has been a fair bit of previous work. So starting with Blum, Dwork, McSherry, and Nissim, they showed that one simple way to design a differentially private mechanism is to take the covariance matrix and add appropriate amount of noise to that matrix, and then work with that. And since differential privacy has the post-processing property, anything I do to that is great. And surprisingly, this is actually a variant. Essentially, this is the algorithm we'll be talking about today. We'll give a new, much nicer and much better analysis of this algorithm. So Frank McSherry, I guess back in the day, proposed using the exponential mechanism to solve this problem. And this was also used in works by Chaudhary, Sarwate, and Sinha, and by joint work with Michael Caprolo and myself. And you can show that the exponential mechanism gives you this kind of a guarantee. So if I measure my error in terms of the 2 norm, don't worry about what that is, but basically my additive error is something like some polynomial in k, and this is probably not optimal, times n. So there's a linear dependence on it. And in fact, there's a lower bound that you at least need a k there. Okay. So this is essentially what we know about the pure privacy case, and this n is necessary and sufficient. For approximate differential privacy, you can get this down to something like k squared times square root n, using techniques from using the work of Hart and Roth, and I guess more recent work of Hart and Roth gets you something like square root kn times some term that depends on the eigenvalue separation. So if you have some separation of eigenvalues, you can get something like square root kn.
So note also, I mean, it's the same bound as above. You just, because you're only talking about k singular values, you can always assume a separation of 1 over k. So if you want to make that a k to the 1.5 or something, I mean, if you want, you can always make the dependence on k worse and get rid of the gap. But this was a side remark.
Okay. So as I said, we'll be using the Frobenius norm measures, or rather the Frobenius norm squared measure. It's, in addition to being nice and intuitive, it also has the advantage that if you get good guarantees for this, they also imply better guarantees for the other measures. Okay. And this is the guarantee we get. So the amount of variance I capture is at most k root n more than the best possible. If you actually cared about the 2 norm or the Frobenius norm, you can get something like, for Frobenius norm, it's square root of that. For 2 norm, there's no dependence on k, it's just root n. And just for comparison, the 2 norm bound, so I guess previous works only gave 2 norm bounds and they all had a dependence on k. We get rid of dependence on k, and I think the more appealing thing is it's both the algorithm and the proof are very simple, and I'll actually hopefully show you both of them today.
So think of delta as being constant here, or how is delta going through the bound?
Say that again?
How is delta going into the bound?
So I'm hiding lots of constants. So it's something like square root log 1 over delta divided by epsilon hidden in all of these. Good. But yeah, if you think of a somewhat nicer notion of privacy like CDP, then you can get rid of the log 1 over delta, but don't worry about that. Additionally, if you have a separation of eigenvalues, you can actually improve these bounds. You can do even better, you can go below this. And moreover, we show a lower bound showing that no differentially private mechanism can do better than this in general. So k root n is what something very simple gives and cannot be improved. Okay, so here's a quick talk outline. I'll first show you the mechanism. I'll give you a complete proof of the utility for the gap independent case. I'll give you a rough, I'll hand wave a little for the gap independent case and then talk about some other results. Good. Okay, so let me start with a few observations. As we said already, the optimal subspace is just the subspace spanned by the top k eigenvectors of A transpose A. A transpose A is the covariance matrix. It's nothing but the sum of xi transpose summed over all the rows. So if I think of the matrix C as my object of interest, it's just the sum of individual contributions. So each person contributes their xi transpose. And if I take out Cynthia's data from this matrix, the matrix A prime that I get, the neighboring matrix, the difference between these two is exactly xi transpose, where xi is the row corresponding to Cynthia. So the sensitivity of this object C is essentially this xi transpose. What do I know about xi transpose? I know that xi has norm 1. And what that means is that xi transpose is a rank 1 matrix whose spectral norm is 1. So it's a rank 1 matrix, only one eigenvalue, that's 1. What that means is that the Frobenius norm of xi transpose is at most 1. So what have I said here? If I look at this quantity C, by adding or removing one person, the total change in this matrix, the sum of squared entries of the change, is at most 1. So now, instead of viewing this, so if I view this matrix as one long vector, I'm saying one person can change the total L2 norm, change this long vector by a total L2 amount of 1, which basically tells me that I can use the Gaussian noise mechanism. So formally, here's the mechanism. I have this matrix, each row has norm 1. I'll compute the true covariance matrix. I'll define the error matrix, which is just essentially constant in each entry. And I just add the two. And now, essentially, the basic analysis of the Gaussian mechanism, going back to a long time ago, tells me that outputting C prime is differentially private. So I can output the covariance matrix. Now you can do whatever you want with it. In particular, you can output the top K subspace of this if you want. So the privacy, as I said, is immediate because this is Frobenius norm 1, gives us a vector. It's a norm 1 change, so adding Gaussian noise of amount 1 in each direction gives me privacy. So let me get to utility. Before I get to that, let me just set up some notation. I'll say pi k is the top K subspace of C. So this is the object I'm really looking for. This is opt. What this mechanism will output will be pi k twiddle. So that's the top K subspace of C twiddle. So the proof is as big as the algorithm. And I'll show you the whole proof here. Linear algebra proofs often get very hard to read because of notation, but bear with me, this is short and it's very simple. So the quantity I care about, this is pi k times A transpose Frobenius norm squared. This is equal to the trace of this times its transpose, which is equal to this quantity here. This is just restating. Now trace has a nice property that it's linear. So A transpose A was C. Let me add and subtract E to it. And because trace is linear, I can write it out as the difference of this trace and this trace. So good. So far I've not done anything. I've just re-expressed my objective function as the difference of two traces. But as we know, any interesting proof should have an inequality, so we'll have one. What do I know about pi k twiddle? This is the optimal subspace for C plus C. So in particular, it's no better than using pi k. So if I had instead used pi k, I would be worse off for C plus C. So I have this inequality. I can replace pi k by twiddle by pi k, and I'll get a greater than equal to here. And now I again use linearity of trace. The first term is what I care about. And I'm left with this trace of the difference of the subspaces times E as my error term. So the total variance I capture is at least the best possible minus this little error term. Okay, so now all I need to do is understand this little error term. So firstly note that these are projection matrices into rank k subspaces. So this is a rank 2k matrix. I've taken some matrix, projected it down to 2k dimensions, so it's a rank 2k matrix. So this is at most 2k times the 2 norm of this matrix. And standard results in random matrix theory tell me that the 2 norm of a random Gaussian matrix is square root of n. So that's it. This gives me that algorithm is at least opt minus k times square root n. 2k times square root n. Any questions? Good. So notice we didn't make any gap assumptions. To answer Rohr's question, there could be cases when you actually, what you're outputting, if there's no gap, you may be outputting something which is very different from the top k singular subspace. But we'll still capture as much variance as the best one. One interesting thing to notice is that I'm not averaging when I define my left-hand side. So this is increasing linearly with m. As you get more and more entries in your matrix, the total variance in the subspace in any probabilistic model is increasing linearly with m. My error is staying independent of m. And it's not hard once you have this to get other variance for the other notions of error. Let me not get into that. Instead, let me talk about the utility, how you prove any bound when you have a gap. Okay, so recall what we proved in that big box was that the algorithm gives me at least opt minus this trace here. So earlier we just analyzed this as saying this is a rank k matrix, this is a small spectral norm matrix, but morally when if your matrix actually has a gap between the kth and the k plus 1 singular value, then it's not easy for a perturbation to change pi k. So we'll use that fact here. So just notice that this is still a rank 2k matrix, so I can actually bound this error term by 2k times the 2 norm of this matrix. Earlier we just bounded the 2 norm by the norm of E, but this actually will be small when there is when I do have a gap. So if we can actually control this quantity, we'll actually get an improved bound. And we are, of course, not the first ones to ask this question. This is an old question in matrix perturbation theory. And what's known as the Davis-Kahn sine theta theorem or variance of that basically say that this error, the difference between pi k and pi k twiddle, becomes smaller as the gap between the kth and the k plus 1th eigenvalue increases. So I have c plus e here, but that can be easily changed to c with an additive square root of n. This doesn't really matter so much because when the gap is less than square root n, the previous bound is actually better. Good. So this nice sine theta theorem, which actually has a very simple proof. If I had 5 more minutes, I would show you the proof of that as well. Basically shows that you get error which kind of decreases with the gap in the eigenvalues. One thing that's kind of very interesting about this algorithm is that if you think of a probabilistic model where so each of these xi's are coming from some low dimensional subspace plus noise, the true gap between sigma k and sigma k plus 1 is actually increasing linearly with m. As I have more and more samples, the covariance matrix is, the unaveraged covariance matrix is increasing linearly with m. So my gap is actually decreasing with m my error is actually decreasing with them, even though the quantity I'm approximating is increasing with them. So I'm getting really, really fast convergence. In some sense. Additionally, if you don't actually have a gap between the kth and the k plus 1th, you're willing to output a k prime dimensional subspace, you can get bounds where this gets replaced by k prime plus 1. So we can also get subspace convergence guarantees using these arguments. So pi k in fact converges to pi k hat. Sorry, pi k twiddle converges to pi k. Yeah. Okay. So that's all I'm going to say about the mechanism and the proof. Let me spend a little bit of time on some of the other results that we can prove using this simple approach. So the first one is an application to online prediction. So consider the following model, so this is similar to the online prediction model that Adam talked about yesterday, where now instead of now in each time step, the algorithm has to produce a k-dimensional projection. Nature or an adversary produces a vector xt, and you get a payoff, which is how much variance of x did you capture. And you measure your regret as what you capture minus what the best k-dimensional subspace could have captured in hindsight. This model was studied by Warmuth and Kuzmin, by Hazan Kale and Warmuth, and by Nee, Kotlowski, and Warmuth. And they've shown various results in this setting. Now, what we do know is that if you have a stable algorithm which has high utility, then you can convert that to a low regret algorithm. This is what Adam talked about yesterday. And it turns out that this noise addition gives me sufficient stability to actually just make that analysis go through. So what we get is a follow the perturbed leader type algorithm, which expected regret is about square root k opt times n to the 1/4. So turns out this is n to the 1/4 away from the best known algorithm for online prediction due to Warmuth and Kuzmin. But Hazan Kale and Warmuth actually left open a question of designing a FPL type algorithm which has good regret guarantees. Their guarantees were much worse than this, and this actually answers an open question of theirs, even if I didn't care about privacy. And in fact, because we are actually adding noise, we actually get privacy more or less for free. So unless opt is really tiny, we get the same regret without dependence on epsilon. And in fact, if you actually want privacy, this n to the 1/4 is necessary. You can't get a square root k times opt in general. Good. Okay, so let me just mention the lower bounds. Yeah.
So actually, which open question did it?
So they had proposed an FPL type algorithm to solve this problem, and then found a bug in it and realized that it was wrong. Then they got something that had worse. So I guess the main point is the Warmuth-Kuzmin algorithm is computationally very inefficient, and so in the online prediction community, they believe it's nicer to have a FPL type algorithm, and they had kind of left this open question: is there an FPL type algorithm for this problem with better regret guarantees? And this improves upon the best known FPL type algorithm.
Where does the n to the 4th come from?
So we had the square root k times n in there that comes from the amount of noise we had. It's really a square root k n times whatever the variance of my noise is. Usually when you're trying to follow the perturbed leader type algorithm, you add noise which is actually fairly large, which is something like square root of opt. Or you pick the noise so as to optimize the error you get from the noise plus another error, that term that shows up. And when you optimize that, essentially the square root n becomes an n to the 1/4. Yes, that's the short answer. Good. The lower bound actually uses techniques developed by Ban, Ullman, and Baden based on previous work on getting differential privacy lower bounds from data tracing schemes. And turns out for k equals 1, such a lower bound follows with not too much difficulty. For larger k, it's kind of somewhat challenging, and we need to use this somewhat counterintuitive phenomena that we call the list culling game. I can tell you about it later, but yeah, I guess I'm going to run out of time. So I guess essentially we can get exactly this k root n dependence for any k up to essentially n. So up to logarithmic factors, all our gap independent results are tight. In fact, yeah. Okay. Good. So that's all I'm going to say. So basically, we gave a very simple noise addition mechanism, which gives excellent utility, which actually gets better when you do have an eigenvalue gap. It also gives new algorithms for online PCA, and we can prove lower bounds for differentially private algorithm that match our upper bounds. So in some sense, at least in this model, we completely understand differentially private PCA. I'll stop here. Thanks.
Questions?
Yeah.
What little c of epsilon delta, the variance of the noise that you're adding?
Uh,
I missed what log on delta or
yeah.
how does it work? Practice. Have you tried it? I
We have
it's
not
easy to
yet
do,
tried
right?
it.
You just add
Yeah.
MATLAB and then kick it.
Yeah, we haven't yet tried it.
Well, Frank and Ilya had experimental results in their Netflix paper.
Mhm.
This is adding a bit less noise, right, than they were?
Right.
Isn't that exactly their argument?
Pretty much. But they are like, well, I don't know. The McSherry-Mironov algorithm is very similar, right? I mean, it's basically the same thing, but more noise, or?
No. So
They did.
all the entries, basically they take t squared now. Basically our noise does not have any dependence. When you have to each of the points, it's normal 0, 1.
But are there rows normalized to begin with?
Yeah, so they do normalize their rows, but then I think they just observe
They
that
add
each
much
entry
noise.
changes by at most 1.
So
they
it's the same algorithm, and the thing is they don't give epsilon delta values. So they just give, they parameterize their bounds by the standard deviation of the Gaussian. So they do implement this algorithm because they just add a Gaussian noise matrix to the covariance matrix, and they plot the error in terms of the standard deviation. So in subset, it includes this algorithm. It's just the analysis is different, or the analysis that they had in mind was different.
So we just need to change the scale on their.
Yeah,
So you can look
relabel
at
the
their
scale
plots
and,
and just change their. No, I'm kidding. Yeah, so I guess we do want to do the experiments. We just haven't gotten around to it yet. Yeah.
So this variant of this algorithm is actually the closest analogy is the DMN.
Oh, that's right.
And you calibrated, it was
Yeah.
the wrong
That-
number.
Of that
Calibrating
the
the
sensitivity analysis in
sensitivity
DMNSS6, this sensitivity analysis from DMNSS6.
Yeah.
I mean, I think, so maybe I would like to remind you, so I think this is the natural algorithm for PCA. It's just that what you guys show is that you can report dramatically better epsilon delta values than we thought before, right? I mean, this is what you do. You add Gaussian noise to the covariance matrix, right? That's what everybody's always been doing, but now you can report dramatically better epsilon delta values.
Yep.
Yes.
And that's the point of this analysis. So in some sense, the algorithm is the BDMN and Mikhail-Mironov and so on. Right?
Yeah.
So it's just you get a much better. You can label
Yes.
the x-axis much better than they could. Right?
Yeah.
So maybe that's a different answer to this question.
And this would be a great algorithm to use concentrated differential privacy and drop the log 1 over delta terms. All right, if there are no further questions, first of all, thank you, Kunal.